Problem number 11, we've got a long straight wire carrying a constant current I and a rectangular loop right below it with a length of 2L and a resistance R, and it's in the same plane as the wire. So derive an expression for the magnetic field due to the current as a function of distance R. In this scenario, we're imagining this wire as an infinite wire. A really long wire would give you the same equation. Even though that's an equation that you probably have saved in your calculator or have memorized, it's important to know where it's derived. So we're going to start this part A by using Ampere's law, which is the enclosed integral of B ds is equal to mu naught I enclosed. And when we are identifying ds, it's always, after we create an Amperian loop, it'll be at this distance, some distance r. So when we do this integral, it'll be the full circumference of that loop, or that the length around that loop, which is 2 pi r, and then the current enclosed is just I. So our equation, which again you probably have memorized, is mu naught I over 2 pi r. The second part is asking to indicate the direction of the magnetic field crossing the loop. So we're going to use the right-hand grip rule. As the current goes to the right, our grip rule is going to show a magnetic field coming out of the page on top, and then it rotates into the page at the bottom. And so we've got dots up here, and then we've got, I'm going to use magnetic field going into the page. Now, if you look at the size of my magnetic field symbols going into the page, the magnitude of the magnetic field is much larger the closer it is to the wire, and it gets smaller and smaller the further away it gets. So this is going to be important when we start problem part C. But the direction in this scenario is going into the page. Part C is to determine the net magnetic flux through the loop. And so I'm going to do part C up here because we're going to need this equation later, or at least be able to reference it later. So what I wanted to emphasize was the fact that we have an increasing magnetic flux within the loop itself. The closer you are to the wire, the greater your magnetic field and your magnetic flux would be, and then the further away you get in your loop of wire, the smaller your magnetic flux will be. So in order to find the net magnetic flux, we need to take pieces of flux within the wire, just one strip at a time, because we know horizontally it'll all have the same magnetic field, but then as we move further and further down, that flux is going to change. So this is where calculus comes into play. We're going to start with, first, we used in Ampere's law the variable r to represent distance. And as we go further and further out along this wire, we get a larger and larger r. So instead of using dl, which is the length of this wire, I'm going to change the variable to dr, and then we're going to go through from the top of the wire all the way to the bottom of the wire, a full length of L. So let's start with a piece of the flux, d flux. We know that's B dot A. And in this scenario, since we're taking pieces of the area, I'm going to put B dot dA. Cosine theta is the angle between the normal on the loop and the magnetic field, which is 0, and so cosine 0 is just 1. We can cancel that out. But the magnetic field is this equation. So that's mu naught I over 2 pi r. The area, we know that the length, along that horizontal length, 2L, the magnetic flux stays the same. But for the height, we're taking pieces of the height, so that's dr. So dA is this second part of our equation. Now we're going to start canceling things out, and because I want to integrate this to find the full flux, I'm going to bring the r out and bring all of the constants to the left. So d flux is equal to mu naught I L over pi, and then I'm going to put the 1 over r dr all the way to the right, and now we can integrate. And when we integrate, we're going through the full flux. And then when we start, I'm going to call it r. I know we don't generally use the same variable in our limits as we do within our equation, but it will make things easier in the future. So I'm gonna, oh, actually no, I'm jumping ahead of myself. This one is at this specific location. And this specific location starts at a distance of L. I think it got erased somehow, but in your worksheet, you should see that the distance here from the wire to the loop is L. So that's going to be the starting limit. And then the ending limit is the bottom of this loop, which is 2L. And then when we simplify that, we get flux is equal to mu naught I L over pi. The integral of 1 over r is ln. And then I'm just going to do this division, even though usually you would subtract your limits, but I know that ln 2L minus ln L is the division of ln 2L over L. That simplifies everything down, and my net flux is mu naught I L over pi times ln 2. Okay, so this is part C, when the wire is not moving. And I'm going to kind of clean up some of these symbols here just because I want to continue writing. In the second part of this problem, we've got the rectangular loop moving away from the wire at a constant speed v directed to the bottom of the page. So now we've got this scenario where my wire is moving downward. So first thing we need to do is indicate the direction of induced current in the loop. As it moves down, we can see visually that the magnetic field decreases. And so to oppose that decreasing magnetic field, we want to induce a current in the wire going into the page. And so if I use a clockwise current, I will create a current into the page, which opposes the fact that the current is decreasing. So I'm going to go to the right, I'm going to go down, to the left, and up. That would be clockwise. And then the direction of the magnetic force. So it's important to note that each side of your wire is going to have a different magnetic force in a different direction. The wires on the right and left, so if you use the right hand rule, my current is going down, magnetic field is going in. I'm going to have a magnetic force going outward. And then on the left side, my magnetic current is going up, magnetic field in. So I'm going to have an equal and opposite magnetic force to the left. So that ends up canceling out this wire, assuming it doesn't stretch or compress at all. And then when we look at the magnetic force on the top, I'm going to have a current right, magnetic field in, so that means I have a force going upward. And at the bottom, doing the same process, I have a force going downward. Now, one thing you want to keep in mind is that because my wire right here is closer to the current carrying wire, the magnetic field is stronger and therefore the magnetic force is going to be stronger. I drew a smaller arrow for the magnetic force downward because it has a smaller magnetic field and therefore smaller magnetic force. So when it says indicate the direction of the magnetic force, it's going to experience a force pulling outward on all sides, but the net force is going to be upward. Last but not least, this is the hardest of all the problems. It says to determine the magnitude of the induced current in the loop as it is moving downward. So we already did an equation for the net magnetic field when it stays in one position. Now we're going to use this same process. In fact, I'm going to start right here. And instead of our limits of L and 2L, we're going to have arbitrary limits of that is with respect to some distance r, because we know that that r is going to increase as it moves down. So let's start with the fact that we've got a flux that changes as we go down the loop of wire. So I'm going to start with my equation mu naught IL over pi. I'm going to integrate 1 over r dr. And my limit for this, I am going to, let me get rid of all of these arrows. My limit is going to start at r. So I'm going to call that distance r. And then my bottom part of my limit, even though I don't know what r is, I know that when it starts at the top of the loop and goes to the end of the loop, it'll be L plus r. So from there, we are going to integrate. I've got flux is equal to mu naught I L over pi, and then I've got ln, and I'm going to write this like this as ln L plus r minus ln r. And the reason why I'm doing that is because when I go to determine the induced current, current is EMF over r. EMF is negative d flux over d time. And my flux is not changing with respect to time, it's changing with respect to r. So we've never done this before, but you've done it in calculus. It's called the chain rule. If I take my d flux dt and I rewrite it as d flux dr times dr dt, that means that my flux is changing with respect to r, but that distance r is changing, right, because we have a velocity, with respect to time. So that mathematically you can see the dr's cancel, but we can use this, it's called the chain rule, to solve this type of problem where we've got two variables that are changing at the same time. So let's start with EMF. I'm going to do the negative d flux over dt. So I'm going to take my d dt and then plug in my flux equation here. So that's mu naught I L over pi times ln L plus r minus ln r. And then I can't forget the fact that I also have dr dt at the end of my equation. And then I'm taking the derivative with respect to r just of this portion. I've got a whole bunch of constants in the beginning, so I'm just going to pull that out. And then I'm going to take the derivative of ln, which is 1 over L plus r minus 1 over r. And then dr dt is a change in distance over change in time, and that's a velocity. So we're not quite done because we have to solve for current. Current is equal to EMF over R. So I am going to just write this out a little bit nicer. Current is equal to negative mu naught I L V, velocity, over pi R, for my resistance, and then 1 over L plus R minus 1 over R. And that would be my final answer. Again, you can just take the magnitude of current. We already established up here that the current was going clockwise, and so this would be your final answer.